Okay, now we're going to go through the practice exam 4. I posted these solutions online to Canvas, and now I'm just going to talk through some of the answers and explain why the answers are correct. So now we're looking at a series of pyridine molecules for number 1. We're asking which one is the most nucleophilic. So nucleophilicity and basicity in a lot of ways have parallels. So a lot of the ways we analyze what's going to be the best base will also tell us what's the most nucleophilic. The only distinction between the two might come down to maybe some steric factors, but in each of these cases the nitrogen will be our nucleophile and they all have the same steric environment. So we'll be looking for different sorts of electronic effects, either inductive or resonance effects, that could be impacting the relative nucleophilicity of these nitrogens. So a lot of the way we can view and rationalize something like this is similar to topic 2, where we looked at activating or deactivating groups, or electron donating or electron withdrawing groups. So in order to make this nitrogen more nucleophilic, we'll want it to have more electron density. So we're going to be looking for electron donating groups to help guide us in our selection for what will be the most reactive and most nucleophilic. So right now we can see nitro is an electron withdrawing group. This is going to take electron density away from this ring, and therefore this pyridine, so this will be a no. If we go to something like C and A, we have two very good electron donating groups where nitrogen will end up being an even better electron donating group than oxygen. And this ends up with DMAP, molecule A. This is our highly nucleophilic catalyst we use in acylation reactions. And A ends up being the best choice. We can see this resonance structure. It's in the 4 position. That lets us put this negative charge right on that nitrogen atom. So that way, if this nitrogen atom were to react with an electrophile, such as an acid chloride or an anhydride or a DCC adduct, we would have resonance stabilization of that positive charge on this tertiary amine attached to the ring. Then we have things like pyridine that'll just be neutral. It doesn't have any factors, so it won't be as activated. And we have the chlorine here that'll probably do a bit of both. It'll probably be slightly deactivating overall due to its inductive effects, and it's not that great of a resonance donor. Number 2 is just, do you know what an imidazole looks like? And the imidazole is this 5-membered ring heterocycle that has 2 nitrogens in it. The other ones we have are pyridine, we have a quinoline, an indole, and a pyrrole. So this is really just about, do you know your different heterocyclic rings? If we look at the reaction between lithium aluminum hydride and a nitrile, we see that we have a sigma bond nucleophile coming out. So we're going to have sigma as the first part. So that gets us down to 2 of the options. And it's attacking a pi system, so we'd want to have a pi star. It's not breaking a sigma bond, so E is definitely the choice here, sigma to pi star. During the Curtius rearrangement, when we heat up acyl azides, this is your acyl azide. This is when we have the rearrangement where the lone pair comes up, and we have this 1,2 shift to kick out nitrogen. This gives an isocyanate as an intermediate, so that would be answer number A. In looking at which of these different carbonyl or imine-containing molecules is the most basic, the best way to rationalize this is which one is either the most electron-rich, because electron-rich systems will have free electrons to grab a proton. I think the easier way to think about it is, let's try to protonate each of these and let's see which one has the most stabilized conjugate acid. Very strong bases end up having very stable conjugate acids. They get to a happy state after they take a proton from something. And we see that we can probably immediately get rid of something like A, because oxygen will be less able to stabilize positive charge relative to a nitrogen-containing molecule like an imine. But we can already see that we're going to have better options down the road, because now we have something like this amidine. I think it's a functional group you guys have not learned, and you don't need to know its name. But we can see that if we were to protonate this nitrogen, now we're going to have the positive charge on nitrogen and have resonance stabilization. But the best one ends up being this molecule has 3 nitrogens. It's called a guanidine. And we see we have 3 different resonance structures we can draw where all 3 of them can put the positive charge on a different nitrogen atom. So putting positive charge on a nitrogen atom is good. 3-part resonance stabilization is even better. 6 is one of our reaction sequences. This one isn't, I think, too bad. It's just, do you know your reactions? The first step is dehydration of a primary amide with P2O5. That turns it into a nitrile. Then we have sodium azide and DMSO. This does a SN2 reaction to introduce the azide into the cyclohexyl ring. Then we have excess lithium aluminum hydride. That's able to reduce both the azide and the nitrile. Nitriles will go to a primary amine. So we have 2 molecules that have primary amines. And then the azide also gets reduced to a primary amine. So our answer ends up being E. Note that B might be tempting, but the nitrile also brought in an extra carbon. So this would have 1 carbon too few. Seven is very similar to one of the problems we had on our problem set, only now we have a different constraint. We only have 1 equivalent of the alkyl halide. This is exactly one of the situations why we don't try to do this reaction between a primary amine and an alkyl halide to try to generate something like a secondary amine. And that's because the secondary amine will frequently keep on reacting to make tertiary amines. And then because all of the products are still reactants, we probably end up with some of the primary amine along the way too. So while B might be the major product, we're definitely going to have some A, some C, maybe even some D. So it's easy to say we're going to expect more than one of these to appear at the end. Eight is also just testing, do we know the transformations from this section? An amine and an acid chloride will react to make an amide. Note that acetyl chloride is a 2-carbon acid chloride, so we're going to put 2 carbons onto the amide. Lithium aluminum hydride reduces the carbonyl of this amide all the way down to an alkyl chain, so we just make a secondary amine. And these are conditions for reductive amination, or sodium cyanoborohydride with catalytic acetic acid that will put on our final benzyl group. So we'll end up with a tertiary amine. If you look at some of the products, we know actually off the bat a lot of these can be removed. All these hemiaminals aren't even stable, and they would never be isolable products to begin with. Nine is interesting because it relies on some chemistry from topic 2. So we have diazonium formation with sodium nitrite. This makes the diazonium. Then we add in copper cyanide. So this is one of the cases where whatever's attached to copper gets put onto the ring. So we're able to make a nitrile. And this has now becomes more useful because we just learned a number of reactions of nitriles with either reducing agents or Grignards. Now we're using a Grignard to do a ketone synthesis. So nothing else in the molecule changes. We just end up making the ethyl ketone starting from this aniline starting material. So now we're looking at what is the polymer that forms. So we learned some of the reactions of alcohols and phosgene in our carbonic acid synthesis section. When you have an alcohol and phosgene, and you have 2 equivalents of this alcohol, we end up making carbonates. So this is the linkage that we will be looking for in the products. And off the bat, we can see we have some of the polymer products that do not feature this linkage. So here we have almost Friedel-Crafts type products being made. So we can immediately say that these will not be the answer. We see that we do have something that looks kind of like a carbonate here. And we definitely have a carbonate here. But note where this next carbon is attached to. Remember that whatever's attached, let me erase this so it's easier to see. Whatever's attached to this carbon needs to be an oxygen. And whatever is on the other side of this bracket is essentially repeated over here. So this bond means it's actually connected to a benzene ring. So that will not be a carbonate that we need. So really we needed to have another oxygen inside the brackets, just like answer E has. So if we look closer, the repeating unit cuts through the carbonate bond, but we do have the oxygen carbonyl oxygen connectivity that we expect. Number 5 is asking about basicity of different types of nitrogen atoms with a short explanation. So we have 3 different nitrogen atoms in this molecule. We have a nitrile nitrogen, we have a pyridine nitrogen, and we have a nitronitrogen. Perhaps the easiest one to maybe guess is that this nitro will not be positively charged at all. It doesn't have any lone pairs, and it's positively charged. So this is everything, has everything going against it. You couldn't get this to react, the nitrogen at least, of a nitro group to react with a proton if you tried. So this brings the argument down to a pyridine or a nitrile. And this comes down to S character. The nitrile is sp hybridized. The pyridine is sp2 hybridized. That means the nitrile is more electrophilic. Sorry, it's more electronegative. It's more electronegative. It wants to hold on to this lone pair that it has, and it'll hold on to that lone pair tighter than a pyridine will. Or conversely, if we imagine protonating each, it'll be worse at stabilizing the positive charge in the conjugate acid. (12A) is reaction between a carboxylic acid and phenolithium. This is maybe a bit tricky because this is just an acid-base reaction. Phenolithium will simply deprotonate the carboxylic acid to make a carboxylate anion that can't react any further. For B, we have the conversion of an acid chloride into an isocyanate. Along the way, we see the carbon migration, so we know this is going to be a Curtius rearrangement. That means we need to add in sodium azide and heat. Here's a reaction with dibol, so it borrows actually I think both of these elements came from a previous topic, but dibol and nitriles, these are still of relevance now. So if we have dibol in a ketone, this can reduce a ketone to a secondary alcohol, and dibol will reduce nitriles to imines that upon aqueous workup get turned into aldehydes. For D, we are making a primary amine. Along the way, we have one good signal for us, and that's this hydrazine reagent. So hydrazine is used to cleave the reaction product from a Gabriel synthesis, and we see that we have the base and the alkyl halide to start with. So that means we need to be drawing in the phthalimide component of the Gabriel synthesis to answer this question. And now we have reaction of something with diethyl cuprate in order to give an ethyl ketone. And the only reactive group we know to do this is an acid chloride. So it's one of the new reactions of cuprates that we learned in this topic. So now we're getting to our multi-step synthesis problems. We start with just a plain benzene ring, and we're trying to add on 1 carbon directly to the ring and 3 more on the other side, while overall making a secondary amine product. The qualifier here is we need to do this with 3 carbon atoms or fewer. So we probably want to think about trying to bring in this piece all at once in some fashion. So there's a number of ways that we could be trying to do this, but somewhere we need to introduce a carbon to the benzene ring, and then we also need to be introducing an amide. So to make secondary amines, we can go with reductive amination, or we could make an amide and then reduce it again. For the answer I'm writing, it's actually probably one of the not one of the shortest ways we could do it. There are many other possibilities here. But just to show a way to bring in a 1-carbon unit using some of the new chemistry from this section, we could brominate the ring with EAS, turn it into a Grignard, and then use our new CO2 reaction to introduce a carboxylic acid. The carboxylic acid will let us couple on our amine component, our 3-carbon amine with DCC. This makes the key amide bond, and then lithium aluminum hydride in workup gives us the secondary amine product. Alternatively, you could do a Friedel-Crafts reaction followed by oxidation to make the carboxylic acid. That would also work. It would actually be one less step. And there's also ways that you could be trying to make an aldehyde and then do reductive amination as well. So here is another synthesis problem. Now we're trying to make a primary amine. So we're trying to turn this alcohol into a primary amine. But the big distinction that you want to keep your eye on is how many carbons are in the starting material versus in the product. So the product has added 1 more carbon. So whenever we need to add a carbon unit, then we need to be thinking we should be adding probably sodium cyanide somewhere. This will both introduce a nitrogen and it'll also give us 1 more carbon unit at the same time. So we can use PBr3 to introduce the bromide. The bromide then gets displaced by cyanide, and lithium aluminum hydride gives us this product in 3 steps. And hey, the colors I used made these starting materials kind of look like caterpillars. It's like the caterpillar ate some carbons and grew a little bit longer. It's like the very hungry caterpillar from Eric Carle. All right, almost done. Now we're getting to the mechanisms of practice exam 4. And this is the amidation using DCC between a carboxylic acid and an amine. To start off this mechanism, we have the carboxylic acid that's acidic and the basic nitrogen from DCC gets protonated. Carboxylic acid rebounds and attacks the activated electrophile to now make an intermediate that has a good leaving group. So this makes our carbonyl more electrophilic. We have this entire urea leaving group here. The amine attacks, we make a tetrahedral intermediate. The tetrahedral intermediate can collapse, and then the DCC anion or the urea anion deprotonates the product to make the final amide. Note you also could have done one of the more concerted departures of the DCC, but this I think is a little bit easier to remember and follow. And the final mechanism is a Fischer esterification. We have the carbonyl of the carboxylic acid. We want to protonate it at the carbonyl oxygen. That gives us an intermediate that has some resonance stabilization to it. If you try to protonate the other oxygen, you don't get the added resonance stabilization. Neutral methanol can attack this protonated carboxylic acid to get to our key tetrahedral intermediate. Along the way, we want to keep the methoxy and lose water, so we need to have a proton transfer to make water into a good leaving group. Then the lone pair ejects water, and methanol from solution will be able to grab the protonated ester to give the Fischer esterification product.